So one thing that's going to make it more convenient when we start adding up a bunch of different areas together to get our approximation is this thing called sigma notation. So like I just said, we're going to be adding a lot of different rectangles together. So we add up all the rectangles together, and then that gives us our area. But kind of writing this plus sign over and over again is going to be kind of tedious and not super precise. So what we're going to do, instead, is have a new notation that is basically a shorthand for adding a bunch of stuff together, and it's going to be a capital sigma. So this is the Greek letter. When it's typed out, it looks like that. When I write it by hand, I do it like that. All right, so that's going to be a capital sigma, kind of a weird E. It's going to be our notation for adding a bunch of stuff together. All right, so let's see what that actually looks like. All right, so let's say we want to add the numbers from 1 to 20. If we write that all out, well, it even stretches out past the slide. You can't even see the whole thing. But there's a pattern to it, so we might be able to just do 1, 2, 3, ... All right, we kind of know what's happening in the middle, 18, 19, 20. All right, so that's really the only ways we could do that now. All right, just kind of writing this out, maybe putting some ... All right, mathematicians don't really love the ... because it's a little imprecise. All right, maybe something weird happens in the ... that we're not aware of. All right, but most times this is decent. But if we want to be more precise, we're going to use the sigma notation. So what is this going to look like using our sigma notation? All right, it looks like this. And I'm going to explain each of the parts to it. So first of all, sigma, this just means add things. The bottom down here, I equals 1, that's your start. The top up here, this is your end. And here is your terms. So what does this all mean? So it says I start at I equals 1. So if I plug in I equals 1, so I'm going to use a different color. If I plug in I equals 1 to I just get 1. And then this is a very kind of computer science-y thing if you've ever coded in computer science. The next thing you do, after you do 1, you add 1 to this. So the next thing you do is I equals 2. If I plug in 2, I get 2. Again, the sigma means I'm adding all these things together. So I'm going to add the I equals 3 term, which is 3. Then it'd be the I equals 4 term, the I equals 5 term, and so on. Eventually I get to the I equals 19 term, which would be 19. And lastly, the I equals 20 term. And that's where I stop because 20 is the last number up there, and that's 20. As you can see, though, this is a shorthand for adding the numbers 1 to 20. So every single time I take the next I term and plug it in here, I just get that number. And then the sigma means I'm going to add all these different entries together. So the top and bottom part tell me kind of what entries I care about. This part here tells me the pattern that they follow. And again, the big sigma is just a shorthand for adding all these things together. All right, so for now, it's kind of understanding the sigma notation is the first goal, and then using it in our approximations is the next goal. All right, so just to go along with kind of understanding the sigma notation, how would you write these different things in sigma notation? So add the first 10 powers of 2. Well, since we're using sigma notation, you know we're going to have that for all of our answers. I want to add the first 10 powers of 2. So we're going to start off the first power of 2, so that's going to be starting at 1. And we're going to finish at the 10th power of 2, so that's going to be 10. All right, so we're going to add up these different indexed terms from 1 to 10. And we need to put here, all right, after the sigma, the kind of pattern that they follow, where everything is just the power of 2, so it's going to be 2 to the I. So if I were to write all this thing out, I'd plug in 1 first and get 2. Then I'd plug in 2 and I, get 2 squared is 4. Then I plug in 3 and I and get 8, and so on until I get 2 to the 10th, which is some number. Maybe it's that, and it might be close. That's the basic idea of our sigma notation. You kind of where you start, where you finish, and then the pattern that your numbers follow. Right. So for this next one, again, we're adding up a bunch of things. We're pretty much always going to start at 1 for convenience, and you can see there's 5 different things we're adding, so we need to go to our 5th term. And what is the pattern that these are following? Well, it's 1 over something. The 1 doesn't change. And this is technically 1 over 1. But you can see the bottom is the different perfect squares, 1, 4, 9, 16. So all these are perfect squares. We take a number and square it, and we get that pattern on the bottom. All right, so this would equal 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, 1 over 4 squared, and I stop at 1 over 5 squared. So you can see how the sigma notation here is actually the same as that middle line. All right, then adding the first 100 odd numbers. Again, you can probably guess. All right, we have our sigma. We start at 1, and we're going to have 100 different entries. All right, so that's our sigma part. And now we just need to find the pattern of odd numbers. All right, it's something you might not have seen before, but all the even numbers would look like that. You just multiply any number by 2 and you get an even number. An odd number, well, you just go 1 away from an even number. You just subtract 1. All right, so this is going to be, that's going to be the first 100 odd numbers. When I plug in 1, 2 minus 1 is 1. When I plug in 2 is next. When I plug in 2, I get 4 minus 1 is 3. Then 5. And eventually I'd get up to 100. And I plug in 100, I get 200 minus 1 is 199. All right, there'd be a bunch of dots in between there. This is the sigma notation for adding the first 100 odd numbers. More often for what we're doing, we're going to go from the sigma notation to what we're adding together. I will do practice with that in class, but going the other way is also something you might have to do.